शेष जापा
Meeting passport, Akansha. Meeting passport.
For floral welcome, I would like to request Professor Anjali Awadhya ma'am to present flower to our Honorable Chief Guest, Professor Ravindra Pandey sir. I would like to request Professor Vinay Dubey sir to present flower to special guest, Professor Mohan L. Verma sir. I would like to request Professor Samir Thakur sir to present flower to Professor Namita Brahmi ma'am. I would like to request Dr. B.G. Sharma sir to present flower to Professor D.P. Bisen sir. So, to know about the workshop, I would like to call Professor Anjali Awadhya ma'am.
Good morning to all of you, all the dignitaries on the dais, Pani sir, Mohan Verma sir, Hussain sir, and Namita Brahmi madam, my dear colleagues, and dear students. So I am here to share the interesting story about the commencement of this workshop. The source of this event was shown way back in 2012 when Professor Ravi Pandey came along with a team of C-Star developers from Italy and Spain to the provision of Shukla University, and a workshop was conducted there. It was thrilling and exciting, but for us, we found it too difficult. We were happy doing experimental physics, and so nothing new started. I even asked Professor Pandey once in utter surprise that why did he shift from experimental physics to simulation and modeling. Eventually, I got the answer based on my own experience. In 2016, when I came to Science College Raipur, I saw that we lack sophisticated instruments needed for PhD students and researchers. I found the answer in simulation. It empowered us to study all about materials using C-Star. Then Professor Pandey found his able disciple, Professor Mohan Verma sir, who was self-taught and quite passionate about simulation. Actually, at the Sri Shankaracharya Technical Campus Lab, we got the real hands-on experience at that time, and we started collaborative research. We even developed a few experiments based on C-Star, and my research scholars and PhD students got support from Professor Mohan Verma sir unconditionally and generously. With two of my research scholars who were associated with NIT, they could submit their thesis only because they were in innovation studies. So the journey began and we never looked back. It really gives me immense pleasure that we from an institute struggling with lack of resources could establish a simulation lab, and with the help and support of Professor Ravi Pandey, Professor Mohan Verma sir, my scholars like Evan, Aarti, Manisha Gupta, Sakshi, and Rashmi, who is the latest entrant, we are in a position to conduct research, guide projects, and inspire students to learn a new skill. This workshop is all about persistence, perseverance, and patience. It was our passion. If we are passionate about anything, we can make a difference. Professor Pandey will be more than happy to know that we could attract faculty members and students from all prominent institutes in Chhattisgarh, along with several states. We had to stop at 120 participants for this workshop as we wanted to give them a real hands-on experience. We have scientists from all over the world, thanks to Professor Mohan Verma for his efficient coordination. And our objective is to motivate youth in learning the arts and science of simulation. Youth is a real resource for any country. I thank my colleagues for in the department for their dedication and support. My students, particularly Vinay, Arbaz, Akanksha, Megha, and all the PG students of my college. Our principal sir, Professor P.C. Sharma sir, for their affectionate and kind support. Thanks to one and all. Enjoy and learn as much as you can. Thank you.
Keynote speaker Professor Ravindra Pandey sir. And she's chairperson of
बोल इसको धो गया चाहिए बस मैं अभी नहीं धोऊंगा क्या बोलता
Respected Mr. Ravindra Pandey sir, Professor Mohan Verma sir, Professor Ravi Singh, Professor Anjali Ahadia, all the colleagues and dear students. It's my proud privilege to introduce Professor Pandey. One thing is common between us that he is the alumni of Dr. Hari Singh Gaur University, and I am also the alumni of that university. And actually, he is a well-known scientist and needs no introduction. But as a chairperson, I formally introduce him. Professor Ravi Pandey is professor and department chair of physics in Michigan Technological University, Boston, USA. He is a fellow of American Physical Society. He has completed his PhD in University of University Sagar, and he has awarded his PhD in political solid state physics from the University of Manitoba, Winnipeg, Canada. And Dr. Pandey's research interests are in the area of computational material physics, which include development of theoretical methods and computer programs, as well as analysis of specific materials and effects. Published 500 research papers in various international journals. His index is 61 articles. 13,266 citation of his publications. Thank you, sir. And this I invite Professor Ravi sir for his keynote.
मादर चल लोग फिर क्या करेंगे
Namaskar. It's really good to be in Raipur because this is my sasural. So I've been again is coming here for ages, and this is like a homecoming. It's Namita and Dr. Besena here in 2012. We did a sort of a workshop, and at the time, Dr. Verma and Keshav Rao is here. Dr. Rao, he asked the question about modeling. And हमने कहा कि यहाँ रायपुर में modeling कौन कर रहा है? But for last 10 years have been a very happy journey with Keshav and Mohan, Dr. Verma and Dr. Rao. We are doing a lot of workshops all around the country. And I think we did Mohan 4th or 5th in Delhi last October. The reason is I really want to come back because this is a home country and I love Pan. So you have to have a energy to get back. But the special thing about Science College, which I did not know, and I think I'll give credit to Professor Anjali, because I was just here for a week and she really twisted my arm to come here for a day. And this is when I talking to my mother-in-law, she said she studied in this college back in late 50s. So it's really good to be here and you should be proud of this institution and this college, the long history. What I do is I know I want to have more interaction, but time is limited because I have to take a train at 11:50. So I'll give a little glimpse, but I promise you I'll come back again and we can have a one-to-one class interaction and in doing it. So only one thing I request, please ask questions. क्योंकि हम लोग जो प्रोफेसर लोग हैं, वो क्वेश्चन जब तक नहीं आते तो मजा नहीं आता है. And I was talking to Dr. Besain yesterday कि कोविड टाइम्स में Zoom में पढ़ाने में मजा नहीं आता आजकल. But thank God it's over. So I will do is the glimpse of what we can do using modeling. And the reason is modeling has become very inexpensive. In using your laptop, you can run simulation. And like Professor Anjali said, I was experimentalist, doing limnescence experiments. And then, in those days, of course, you have a problem. I was in Delhi and then computers were coming up. And when you're young, you jump into the river, tairenge ya dubenge. But so it's a good journey. And thanks to Chairperson, Professor Namita, I did not know about my statistics. But when you do a good work, people cite you, so you feel proud of your education, your gurus, your colleagues, your students. So let's start. I realize the title of this whole workshop is Materials for Sustainable Development. So what I do is first 10-15 minutes, I'll give you a little introduction and then I pick up an example. And uske baad we'll have a question answer. Are you all comfortable with English or should I do hybrid? Hybrid, okay. So this work, you can see here, Geeta is one of my students, Dr. Odegaard is my colleague, Ching is a student and Dr. Lau is my colleague. So it's a collaboration with we have done this work, recent work. So I come from Michigan Tech. And Michigan Tech is like a UP of a USA. It's way up in north, you can see. But the best part is I don't know if you heard Lake Superior, Meethe Pani Ki Jheel is one of the largest. So Michigan Tech is close to it. And because of the sort of lake, we have between summer ke baad, fall season aata hai. Trees change color, becomes beautiful. But we also have a very cold winter. So for fun, students make snow statues. So 3 days ago, I was in -20 degrees Celsius. But that's fine. Everything is warm and this thing. But this is to me is a blessing, 30 degrees Celsius plus. So This is the message I would like to give. What do we do? Simulation and theory. So the hypothesis is fundamental understanding and theoretical foundation of interactions. Sorry. And from interactions, we can extract information about electronic, optical, magnetic properties. And once we have it, we talk to our experimental colleagues, and उनसे बात करके उनके collaboration में we can really move forward for applications, which is the sustainable development. So the key thing is, what is the structure? And once we know the structure, what is the property? So this is the sort of our aim is to understand for any given material. Our advantage क्या है कि once we know the material, like sodium chloride, which is well known, so we use our model elements to test how good metal elements are. And once you have it, then you can move to predict the properties, like graphene. 2D materials का जो आजकल नैनो टेक्नोलॉजी में आ रहा है. Like Professor Namita said, I've been around for a long time, almost 35 years. But what I've done in my career is every 7-8 years I switch the area using the same tools. We call it English में a 7-year itch. So instead of working the same area for 35 years, I've been moving around. So I started the bulk crystals, okay, especially oxides, nitrides, so-called chalcopyrides. Then moved to clusters, then nanostructures. Then we had 2D materials. But this time I will not talk about it. My heart is on nano-bio interaction. क्या हो रहा है कि you have now is, as you know, you call to your parents, and now you have the phone. They become smaller and smaller, but more powerful because of nanotechnology. अब क्या होता है ये फोन गिर जाए? जो magnetic particles they come out in the environment. आप उसको inhale करते हैं, तो उसका body में क्या interaction होता है? क्योंकि they are all foreign particles. So we are looking at the interaction of these particles with DNA, protein, amino acids, and so on to understand the inflammation inside the cell. Are they going to produce cancer or not? That's the aim. But today I'll pick up some of the bulk materials. So as we know, what is sustainable development? Is the key thing is coming out is that needs of the present. Switch the full screen. But the key thing is the future. Is basically without compromising the ability of future generations to meet their own needs, especially the future is you, how to proceed. And since we are in physics, we are coming from the physics of materials. Key thing है कि how to sort of manufacturing of materials, products, transportation, energy, water resources, and of course education. And if you go back to look back the history, really the materials are coming up, which go back steel grinders and skyscrapers. Minimum space, maximum capacity. Then we move on to aluminum alloys, especially the aviation, the lighter planes. And then, as you know, this is nothing but silicon technology. That's sort of examples of this thing coming in the information. So I'll focus on, give some examples, but because of again time limitation, I'll just pick up the one of the examples of lightweight composites. NASA has funded a project for us the next generation, especially the Mars exploration. They call deep space exploration. How can we make new lightweight composites? So the tools. So this is sort of a cartoon. Just give you idea about what is out there available. अगर आप यहाँ से देखें, this is distance and this is time. And we go from this way. So if you look at the engineering design for structures, and the properties they are looking at so-called the mechanical property. The mechanical response of the materials opposite to the external factors. And we further come down, the reason you have is called angstrom and nanometer or femtosecond or picosecond. We are using the tools of quantum mechanics. Really looking at atom by atom, how do they interact, और उससे उनका response क्या होता है, using our Schrödinger equation, जो आप लोगों ने पढ़ा होगा. So there are a couple of slides जो theoretical हैं equations की. So one of the example is called density functional theory. Simulation आप करेंगे तो DFT is the key word. Is the approach we understand the properties of materials. So if we assume this is our real system, nuclei हैं, electrons हैं, and of course your protons and neutrons. But here we are saying nuclei, the larger ones, and then smaller dots are near electrons. So you have to start with some approximations. It depends on your physics intuition or physics knowledge. ये मालूम है, if you remember Born-Oppenheimer approximation, कि nuclei are larger, electrons are lighter. So what we can assume is nuclei motion and electronic motion, they are decoupled. Because if nuclei moves, what is the response to electrons? But electrons are very, very light, they move fast. So what's the response to nuclei motion? So instead of considering in one part, we are doing part A and part B. So once you decouple it, so we have so-called non-interacting system. So electrons are moving in the field of fixed nuclei. That's the basic assumption. So we have equation. If you remember Schrödinger equation, Hamiltonian wave function, energy wave function, H psi is equal to E psi. और Hamiltonian क्या है? Is a kinetic energy term and potential energy term. So physics of the system is in the potential energy term. The kinetic energy term is simply H square, delta square over 2m. Simple. So this V effective, which is the potential term, has different components. If you look into it, this is simply a charge. This is a small r is electron, big R is the nuclei. So you have Coulombic interaction. Then you have so-called the electron-electron interaction. So you have nr is the electron density over r prime is the distance. And then we have, because if you remember Pauli's exclusion principle, two electrons in the same state, they don't like each other. So we call exchange. And then also when electron is moving in the field of all the electrons, they have some correlation. We call the term EXC. So in all our simulation, what we want to do, if you remember the variational principle, okay, so you minimize the energy with respect to position coordinates. And that is, you can see here is dE over dr is 0 means there is no slope. So you have the ground state energy, or we call equilibrium configuration. That's what we do simply. How to get equilibrium configuration. And it takes years for a student to find it because it's a complex process. It's a lot of calculations are needed. But the DFT, what it says, if you have the ground state energy, so you have the electron density. So this energy is a unique functional form of the electron density. That's why density functional theory. That's well known. So how do we do this calculation? So what I especially start with the student, consider is a black box. आपको theory कुछ नहीं मालूम है, but let's start doing calculation.
Good morning.
So it's like a zigzag path. Once you do some calculation, कुछ idea आपको आता है, then you move on and understand theory. Then you come back and do more calculation. Now you understand. अगर पहले आपको theory पढ़ा देंगे तो बोलेंगे क्या हो रहा है? Because you don't have feeling about the system. So this is a black box approach. And if you remember, I said is electron density. So if you take a molecule, say water, H2O,
क्या कह रहे हैं?
उसके लिए आपको educated guess चाहिए. तो उसके लिए क्या करेंगे? हम taking hydrogen atom to an oxygen. So we have the electron density of the atoms we bring in. Because H2O and it's a solid ice is going to have slightly different electron density. But this good starting point is atomic density. So we start with some initial guess, NR. Then you calculate the effective potential, solve the Korn-Sham equation. Again, you calculate the energy and density. So this is called a self-consistent approach. So आपने एक electron density start किया, you solve the equation, you have new electron density. So what you want to do, find out कि जो पुरानी है, जो नई density है, उसमें difference क्या है? And difference is very, very small. Then you say my calculation is converged. And it takes a lot of time to do it. So once you have it, so you have the ground state electron density. And you're set for properties. So this is one example. कि first question आता है experimentalist का. Professor Anjali बोलती हैं, आपकी calculation कितनी accurate है? How much confidence do you have? So we had done some calculation. This is a carbon nanotube interacting with a DNA base called guanine. And you can see here, it takes 400 of electron volt. We can calculate it. Because of, again, the computational power, this can be done very easily. So experiment is the happy, yeah, we can do it. Because they also have experimental errors. And those errors are 1/10 of electron volt. So we are doing much better than experimentalists in this sense. So you do all this simulation. So students come बोलते हैं कि you have to connect to the real world. What we can do to help experimentalists. So these are some of the examples. Once I said is we have the equilibrium configuration. So we have structural properties. We know the lattice constants. So correlate with experiment is we have X-ray diffraction. So Professor Anjali does X-ray diffraction. We do calculation and see how good they are. Okay. And then nowadays also we have high resolution transmission electron microscope where you can see really the atomic configuration. So you can compare it. Then we have, once you have the structure, if you remember the force. Okay. And force is, if you take the further derivative, is the second derivative of energy. So we term as a Hertzian matrix. So once you have it, what you can do, you can calculate the frequencies. From frequencies, we can relate with the infrared experiments. You shine the light, the system absorbs the light, and it starts vibrating. So from our frequency calculation, we can compare what is the absorption peak is. Same with the Raman. Raman is scattering of photons. So we can also do the Raman calculations. And then in looking at the mechanical properties, we can calculate the called bulk modulus. This is sort of an average response of the material with respect to external pressures. And then of course we have the elastic constants. It tells you about the how stable your system is. And then finally we have called equation of state. This is a thermodynamic variable where you have pressure, temperature, volume. And you connect it to high pressure phase transition. For example, sodium chloride. You take it, apply the pressure. It goes because of, again, it become more and more dense. It moves to cesium chloride structure. It can become a metal. People do the experiments, we can do the calculation. So this is a structure component. But the most interesting thing is what is the electronic structure? Because अगर आप नई generation photocatalysts बना रहे हैं, so you need to have electronic information, which is more important. And that's what I think workshop is focused on, electronic structure thing. The key thing is the density of states or band structure. So you have the system, you solve it, so you have to be called eigenvalue spectrum. If you remember Holmholm gap or valence band or conduction band. From here, you can do the optical absorption. So optical absorption, you shine the light. Once there is a gap, it absorbs the light gap, you have the absorption peak. So we can correlate with the absorption peak to our band gap. Then we have is so-called X-ray photoelectron spectroscopy. X-ray has again high energy photons coming in, and they knock off the electrons from the valence states, which you can again correlate with it. Then we can calculate so-called the effective mass of carriers, either electron or holes, which tells you about the carrier mobility, which is important for the devices. Is there any question there? Or? Question hai kya nahi? Then we have so-called this polarizability. Do you remember the definition of polarizability? This is a flexibility in the electronic cloud. Because the more flexible the electronic cloud is, it's going to be more responsive if you either apply the electric field or magnetic field. From there, we can calculate so-called the non-linear optical properties. And then we have, if you do the so-called the spin polarized calculations, they can talk about the magnetic properties of the system. Is it ferromagnetic, is it antiferro, ferri, you can predict it. This is the most important slide. I think you have to remember. Then we talk about it, what is the length scale? And I want you to be aware of this length scale. When you talk about the electron transport, we are talking about the Fermi wavelength, which is 1/10 of nanometer. Or we have scattering length is about 10 to 100 nanometers. We talk about thermal transport. Basically, we have the thermoelectronic electric devices. So we are talking about the mean free path of phonons, which is the lattice vibrations, is about 100 nanometers at room temperature. For optical interaction, they come again is about 100 to 300 nanometers. Magnetic interactions, you have so-called exchange interaction is about again a nanometer. So whenever you see nanometer means we are talking about the quantum mechanics. And that's the key thing. But we have again so-called dipole-dipole interaction, we have fairly long range into microns. So, sorry, that's my hand. Example, this is a nanobio interaction term. So one of the experimentalists, Dr. Hussain at the Air Force Lab in the US, he showed me this graph. So I don't know if you know dopamine. When we are happy, dopamine level becomes high. Okay. That's one of the neurotransmitter. So doing some experiments in a mice, चूहों के cells में, and he found is, so this is a level, and this is the different cases. He uses the manganese nanoparticle, which are in our mobile phone. Okay. So you can see with time, the level goes down. But if you use silver nanoparticles, there is some reduction, but not that significant. So he said, Ravi, can you tell me why manganese is affecting the dopamine level, but not silver? He said, okay, let's do it. So we go back to drawing board. Is the question again is always remember research ka first and foremost you have to ask question. What is your hypothesis? Okay. Without it, research is not possible. You're going all over the place. So it's called one of my colleagues, Dr. Arora. She said is first thing is gather the information. Now you have Google Guru. You have, I don't know if you heard the new thing is Chat GPT. It's coming up. So you gather information, read the papers, and then ask the question. Simply ask the question is, why do Mn nanoparticles deplete dopamine level? So we said, okay, we have to find out what kind of the nature of interaction is. So we do this so-called the energy surface calculation. We pick up a nanoparticle, a model. We have dopamine molecule and see how they interact. And always remember, if you're an experimentalist or you're a simulation person, you have to do control experiment. So Dr. Hussain gave me manganese and silver. So we looked into electronic structure. Manganese is 3d5 4s2. Silver is 3d10 4s1. So we said, let's find what is control, which is slightly different, but more or less similar number of atoms. So picked up aluminum because it has 3s2, 3p1 electronic configuration. And then we calculate so-called the interaction strength. So this is again is a simple cartoon. You have these nanoparticles and dopamine is coming in and they interact with nanoparticles. So we calculate at each point this energy surface and bringing in different sites. And you can see here is if I start from very far away, energies start from here, this is my 0. I bring in, they start liking each other, energy goes down. But again, is at some point, the electrons of the nanoparticle and electrons of molecule, they don't like each other. So energy rises. And you can see nice energy rise. So this is we call the most stable configuration at a given site. Once you have it, you calculate the binding energy. So you have the complex, you have the nanoparticle, you have the molecule, you subtract and get some numbers. So a striking thing you can see here is manganese loves dopamine. Binding energy is 1 electron volt, which is very, very high. Silver, more or less, and aluminum simply doesn't like it. So you can see the advantage here picking up the reference point. Because if you see manganese, silver, okay, see fine, but so they have a 3D, S type, and P is simply doesn't like it. This gives you a reference point. So you understand why. And that's the best advantage of being a chemist. Some chemist friend ke paas gaya, humne kaha, what is going on? He said this is very easy. It's we called hybridization. If you see here, manganese, it's a D, and this is dopamine. Dopamine is a carbon atoms, is a benzene ring. So you have px and py in the plane, but pz orbitals are perpendicular. So these pz orbitals interact with d orbitals. And PD hybridization is very, very strong, and they very strong overlap. Here we have PS is very, very small. You can see the binding energy also. And the PP, it doesn't interact. You can see here the magnitude of the binding energy and the physics or chemistry of the system are giving you the explanation. Why does it work? So coming down to is the interaction is very strong with the manganese. Manganese sees dopamine, forms a very strong conjugate, and of course dopamine level goes down. Silver is less, and the aluminum doesn't interact. So thus I gave you one example. How do we interact, do the calculation and work with experimentalists to provide the interpretation of their results. That's the key thing. Now here I pick up, so we had done a lot of work from composites, so for photovoltaic materials, new generation, and then again you have the water splitting for photocatalytic materials, and then we had done some lithium-ion batteries coming up. But because of the time, I'll just pick up one example and go quickly to talk about the lightweight composites. So what is a polymer composite? So always remember is you're doing physics, but you have to like chemistry also. Okay, because now is an interdisciplinary field. Composite is nothing but we have the matrix, which is a polymer, organic molecule, and you have the either nanomaterials or any other thing coming out, and they provide the interface. And if you look at the interface, this is messy. Spaghetti or Maggi noodles. Reason is we have all sort of interactions are going on. Okay. But the advantage with our quantum mechanics is we can study each and every interaction. That's we have the strength. So what is happening here is in a composite material, this interface dictates if you apply the pressure, how does it deflect it? Okay. So if you look at the definition, we call is the so-called weak interface, means it has a low strength. Okay, at the interface, and then you have a strong interface, which is called the high strength. And if you remember the brittle, pencil लिए आप उसको तोड़िए खट से टूट जाती है. So in a composite material, you don't want to have it. You want to sort of have flexibility. So if you look at the experimentalist, if suppose Dr. Anjali, Professor Anjali wants to make this sample, you can see you have the 10 fiber options, 30 matrix option, and then you have so many permutation combination. And if you want to manufacture it, then again you have different processing conditions. So experimentally, there is a lot of variables are there. So where we do fit in, so our idea is take all this combination and see if we can tell experimentalists just pick up 4 or 5 combination. So it becomes life easier for them. Okay, so that's why we call it a down select materials from all the combinations. So this is the workflow. So this is we are using a polymer with a graphene. So you start with the so-called the monomer or single molecule of that polymer, because polymer is if it's a poly, काफी है. So we pick up all a single molecule and then we combine with the graphene. You apply some periodic conditions and calculate. Always comes back to this graph. Remember, what is the equilibrium configuration? So for this case, so you have graphene sheet and you have molecule. The question is how it's going to come down and sort of anchor on the graphene. So you can have a so-called the flip up configuration, flip in, the vertical or in plane. So you do all this combination, and that's why you have to have a good student who can do all these calculations. And you calculate the interaction energy. So you can see here different orientations. This is the interaction energy, and sort of tells you that in plane configuration is going to have strong binding. So that's the one step. Once you have it, then you pick up a lot of different polymers or monomers. So the matrix again, you have to understand now the chemical engineering. They call hardener and resins. So resins are the host, and if you add hardener, it becomes hard or strong depending on the processing conditions. So picked up a lot of combinations and you calculate the same interaction energy and comes down to it. So you see there is a trend. But as a physicist, you want to know कि क्यों हो रहा है. But the best thing is what is a chemical bond, which comes from density of states. So what you find here, there are two cases that you have a lot of the carbon and hydrogen bonding is there. You can sort of see all these peaks coming from the different atoms. So first thing is the carbon and hydrogen, they hybridize with each other, which makes sense. Carbon is coming from graphene and hydrogen is coming from the polymer. But only thing is that we find is going from this one kind to other kind. You can see these little peaks here, the arrow. Here we don't have any peaks. So the reason is one of the polymer has oxygen. And this oxygen interacting with graphene induces what we call hybridized states. And that explains the variation in the energy. So far so good. But when you talk about the engineer or the chemist, they say, what does it mean? Okay, can you calculate the mechanical response? So you talk to them, they have different language. So they do called pull-out test. So they have this composite and they start ripping it apart. Okay. And at one point it's going to break. So they call is if you can see here, the separation point. So they are applying the force. This is the strain, which is the variation in length. So it's sort of force you're applying more and more, and at point it separates. So they ask is, can you calculate separation point? So you go back and see how can we simulate. That's easy. We thought the student said beta. I take the graphene and start moving the monomer. And at each point, calculate the energy. Screen per red color. That's something. So, and if you remember energy you have, you can easily calculate the force, which is derivative of energy. And once you have force, you have stress. The stress is force over area. So you have the so-called the stress, then you have strain, and from you can calculate the so-called the stress calculation. So we did this calculation and we found indeed there is a difference. So you have the force, strain, and you can see the resin is more or less same, but the critical thing is coming out the hardener, which sort of provides you the one is good or one is not good in that sense. So you can see here it's easy to now provide experimentalists which combination is going to work for you instead of all those combinations. What is the message? Is okay?
Sir, actually there is some issue. Someone has started skin annotation.
So from all this combination, we have to collect the information. And as a physicist, the key thing always remember is how to present the results. And you can see here is this is a mechanical response. This is strain and this interaction energy. And you plot all the predictive properties in terms of these the bars. And you can see here, this is more or less same combination, but this one combination is really different from other three, which is much more appropriate to manufacture lightweight composites. This good is a single molecule in graphene. But if you go to Professor Anjali said, so what? My polymer has a lot of molecules. Can you scale up? Okay, that's a challenge. So challenge is now is what we call, we have so-called multi-scale modeling. With the quantum mechanics and whatever the power we have, हम लोग कुछ ही atom कर सकते हैं, 100 atoms, 150 atoms, बस. But polymer is thousands of atoms. So we went to another method called molecular dynamics method. So instead of calculating the Schrodinger equation or Kohn-Sham equation, we solve the Newton's forces of the mass times acceleration. And the key thing, you need to know the interaction parameters, which you can get from quantum mechanics. So I told my students, and so she said, okay, let's do it. So from 100 atoms, so we are going to now 45,000 atoms. Okay. An experiment is happy here now, it makes sense in that sense. So again, you have to chart out what do you want to do. That's a key slide for your PhD if you want to do how to do calculations. It'll take a few minutes to do. So this is the monomer, single molecule. You have to mix everything and generate the polymer. Once you have it, then you combine the graphene. So you have the composites. But now you have to heat it up. Because the chemical process, you heat up the polymer composite, you make it. So you heat it up, do the sort of annealing. Then there's a process called equilibrium. And now you have the composites. From here, then you do the pull-out simulation. So you're trying to pull it out to see. So look at the left and right. Okay. So this is an animation. So I'm pulling it out, but they more or less stick to each other. But the same thing on the right hand side. Yeah, just a minute. You can see it breaks. Yes. Good. So the person knows what is MD is. So as you know, is you have to first start with the NPT to equilibrate it, and for real, then you have move to NVT because you are changing the volume. So the both combinations. So can you tell me what is the difference between these two cases in terms of physics? It's intramolecular bonds. First case, they are very strong. No matter kitna pull kijiye. Second case, they are weak. And if you see, it reflects in the curve. Stress and strain. The first curve is, you can see, it breaks, but the second you can see it takes on, carries on, and then you have question of state and you find out exactly the number. And the key difference is here, you can see the toughness. The first so-called epoxy is about 37 millijoules per meter cube, but for BMI is a 98. That's a big difference. So all this combination, I'm going to tell Professor Anjali is don't do epoxy, use BMI. So you can see now is the power of prediction and the guidance to experimentalists. What to choose to do further experiments. So our job is done. So in summary, one example is said. So these are again it's a molecular level calculation, both quantum mechanics and atomistic, which is a Newton's law of classical equation. We sort of we have found out that one of the particular example of polymer works better than others. And then it becomes to guidance to experimentalists to do further. So I hope in 30-35 minutes to convince आपको किया कि simulation and modeling does play a major role. And both nanobio, prediction of properties. I have not gone to electronic properties because Professor Verma will talk about it in that sense. So again, I'm very thankful in my career that the gurus, the postdocs, colleagues, students have really helped me a lot in moving forward. Thanks to Anjali also inviting me, talking to you. And really is my heartful thanks to Professor Verma, who really convinced me to come here, even for a few hours. And of course, thanks to all of you listening my little talk. Thank you.
किसी को कोई क्वेश्चन पूछना है?
क्वेश्चन नहीं है मतलब आप लोग
यस क्वेश्चन
सब लोग पूछते हैं what is the difference between say America and India
यस
आगे बच्चे
Question is a question. Please ask questions. Teacher, always
yes.
Instances that you used a term like binding energy and interaction energy. Same. And she's the same.
binding energy, if you talk about the solid, if you remember, we have the cohesive energy. It talks about the material itself. And interaction energy represents interaction between two entities. I means they like each other, so they don't like each other.
So there was a PG student, so they will not.
Just want to see how this translates.
Zyada questions होने चाहिए आपके पास. PG students हैं. Actually, some experiments based on system. So
That's fine to see your size. Just like good questions, sir.
molecular dynamics equation, are they free or are they system or we have to purchase it?
तो पहले एक क्लास है हमारे मैडम का. Always remember, we are Indians. Although I'm in the US, but I'm in India. So we are all looking for the free stuff. So in my life, I have not paid a single money to any programs. If you need here, you sit down and you make your own. So Verma, Kishore also can tell us we always look for the free stuff. So atomistic modeling is a free code. They're out there.
What is the relevance of these polymers on graphene systems to strain sensor applications? Did you calculate?
Question is yes. So these are the two different things. Position, we are looking at the strain, which is a strain sensor we apply strain to the electronic device. Is going to sorry. So the last question is from send me Mr. Vishwas an email. Send you some of the PMP codes. You can do the search or chat GPT now. PMP codes and you can see the information.
I request principal of our institution, Professor PC Chaubey sir, and Professor Ravindra Pandey sir on the dais. And all the dignitaries.
Convener of the.
I welcome Prince.
उधर से
I welcome principal of our institution, Professor PC Chaubey sir, and I would like to request and invite Professor Vinod Dubey sir to present flower to our principal sir. I would like to invite Principal Sir to present a memento to Professor Ravindra Pandey Sir. Yes, ma'am. I would request Professor Anjali Vawadhya ma'am to present memento to Professor Mohan L. Verma sir. I would like to invite Professor Vinod Dubey sir to present memento to Professor Namita Brahmi ma'am. I would like to invite Professor Alok Lucas sir to present memento to Professor D.P. Bisen sir. thank you, Professor Ravindra Pandey sir, for your valuable information regarding the sister program, and thank you all the dignitaries and participants for the inaugural of this program. Now it's time for tea break, so all are requested for to go to our department for the tea.